Hello everyone, hope you're having a wonderful day. Today we're going to talk about equilibrium in gas systems. So if you have a reaction that is reversible and it has reached equilibrium and your reactants and products are gaseous. And so in any gas system, in any gaseous equilibrium, the concentration of the substances can be determined by their pressures. We know from the ideal gas law from PV equals nRT that we can relate pressure to moles. They're directly related. Or we can relate pressure to molarity, because if you take the volume on the bottom here, so N over V, moles over volume, that's molarity. And so it's directly related to the pressure. And, if you remember when we were doing Dalton's law problems back in chapter 10, we would relate the mole fraction to the partial pressures as well. So instead of using, Kc, where it's the equilibrium constant in terms of concentrations, so it's the concentration of the products over reactants raised to the power of their coefficients, we can express it in terms of Kp. So there's an equilibrium constant in terms of partial pressures as opposed to concentration. So if you see K with a C there, we're talking about the regular KEQ, the regular one with molarity. If you see a P there, then we're talking about gaseous substances, and we're talking about the equilibrium constant in terms of partial pressures. And again, we can relate the two because of PV equals nRT if you're talking about gases. So we're going to write the equilibrium expression for PCl5 yields PCl3 plus Cl2. And I'll do both Kc and Kp. So we would ignore this because it's a solid. We'd ignore this because it's a liquid. Remember, we only talk about gases and aqueous substances when we're talking about K. And so if we're doing good old Kc, it would be the concentration of the Cl2 just raised to the first power. If you were doing Kp, you'd do the same thing, but instead of brackets for concentration, you use P for partial pressure. So you'd say it's the partial pressure of the Cl2 raised to the first power. And that's it. Let's look at the next one. CuSO4, that should say solid there, yields CuSO4 plus 5H2O. So this is a hydrate being heated, and you're getting the anhydrous in the gaseous water. So normally we would ignore this because it's a solid, ignore this because it's a solid, and just focus on the gaseous water. So Kc would be concentration of the H2O gas raised to the power of its coefficient, so raised to the fifth power. If you were doing Kp, then it would be the partial pressure of the H2O raised to the fifth power. All right, let's look at this here. It's telling us that Kp for the dissociation of N2O4, so N2O4 dissociates into two NO2s, at 25 Celsius, the equilibrium expression in terms of pressure is 6.75. We want to know what the Kp is for this reaction. Now, how does this reaction relate to this one? It's the reverse of it. And so if you were doing K for the reverse reaction, it would be 1 over K for the forward. K reverse equals 1 over K forward, just like you would do with Kc. So Kp for the reverse reaction would be 1 over 6.75, which would equal to 0.148. And just to prove to you that it would be 1 over that, or the reverse of it, if you were to write Kp for the reaction that we want, it's the concentration, it's the partial pressure of N2O4 divided by the partial pressure of NO2 squared. If you were doing it for the above reaction, the one that was given to us, Kp would be flipped, it would be the partial pressure of the NO2 squared divided by the partial pressure of the N2O4. So see how these are flipped, so it's 1 over the other. All right, how about the next one? We want the Kp for this reaction. So how is this reaction related to the one that's given to us? Yep, it is half of it. This is half of the reaction that's given. So how would you do K for half a reaction? You would put it to, you would take the square root of it, or the power of 1/2. So K would be equal to 6.75 to the 1/2, or square root of it, which is 2.60. So again, Kp is very similar to Kc, just terms of pressure as opposed to molarity. Now, what is really the exact relationship between Kc and Kp? Well, we can derive it, or you can memorize it. So let's look at how you would derive it. We know that the ideal gas law says that PV equals nRT. If you were to solve for P, it would be nRT over V. This right here is molarity, or concentration. So P is equal to the concentration times RT. So then if you want to relate Kp to Kc, you'd say that Kp is equal to Kc times RT. So there it is, Kp is equal to Kc times RT. We'll just add one little thing. RT is raised to the power of delta N. Delta N is the change in moles, in gas moles, from products to reactants, or reactants to products. So delta N is the number of gas moles in the products minus the number of gas moles in the reactants. You can think of it as moles or particles. So you can memorize this one. You can memorize this one. I think one of them is in your green sheet, so you can check which one is there and just go with that one. And again, delta N here, or here, is the number of gas particles in the products minus the number of gas particles in the reactants. So when would Kp and Kc equal to each other? That's when delta N is equal to 0. Which means what? That means same number of gas particles in reactants and products. So for example, you start with 2 moles of gas on the reactants, you end up with 2 moles of gas on the products, then your delta N would be the same. So let's try this one here. It says, what is the value for K when Kp for the reaction between hydrogen and nitrogen to yield ammonia at 25 Celsius is 6.0 times 10 to the 5th. That's a big number, so that tells us this product figured. So whenever you see K or Kc or Kq, typically those just mean in terms of concentration. Whenever you see Kp, that means in terms of pressure. So you can use either one of those two equations that relate Kp with Kc, whichever you prefer. I'll use this one. Kp is equal to Kc times RT delta N. So Kp is given to us as 6.0 times 10 to the 5th is equal to Kc times R is 0.0821 atm times liters per mole Kelvin. Temperature is 298 Kelvin. And then that's raised to the delta N. So let's look at delta N products. We have 2 moles of gas. Reactants, we have 4 moles of gas. So 2 minus 4 is -2. So this whole thing is raised to the power of -2. If you plug it into your calculator, you get Kc is equal to 3.6 times 10 to the 8th. As always with Kc or Kq or Kp or Q, any of those, we don't really care about the units for them. The next 3 problems have to do with this reaction here. So NH4HS decomposes to form ammonia and H2S. So let's look at letter A. It says solid NH4HS is placed in a flask at 25 Celsius, so room temperature. At equilibrium, the total pressure inside of the vessel is 0.659 atm, and some solid remains at the bottom. So, this is an equilibrium, and so at equilibrium you still have some solid left, and you have some of these gases as well. We want to calculate both K and Kp. So we want it in terms of molarity and in terms of pressure. Now, depends on what information you're given. That tells you which one you calculate first. In this case, the only number other than the temperature, which we don't really use, well, sometimes we use, but the only other number is atmospheres, so it's pressure. So that tells me I'll probably calculate Kp first and then get Kc or K from it. So let's start by writing the Kp expression for this reaction here. So Kp is equal to the partial pressure of NH3 times the partial pressure of H2S. And I don't include the NH4HS because it's a solid, so I don't care about it. All right, well, I don't have either of the partial pressures, so I need to figure something out in order to find it. Now, what I do know is that at equilibrium, P total is equal to 0.659 atm. Now, what is P total equal to? What is the total pressure? Well, the total pressure is the sum of all the partial pressures of the gases. So I have 2 gases here. I have ammonia and I have H2S. So I know that the partial pressure of ammonia and the partial pressure of H2S together are equal to 0.659. Because my reaction is solid, it's not included in there. What else do I know? Well, I know that initially I don't have any of these gases at the beginning of the reaction. I just have the solid. As the reaction goes by, I start forming these gases, and for every mole of ammonia that I form a mole of H2S. So for every atmosphere of pressure for ammonia, there's going to be an atmosphere of pressure of H2S. Remember, partial pressures are related to moles. And so because this is a 1-to-1 ratio, these are going to be the same partial pressure at equilibrium. And so I can say that the 0.659 atm is equal to x plus x. They're both x's, and so partial pressure of NH3 is equal to the partial pressure of H2S, which is x, which is 0.659 divided by 2, which would be 0.3, if you round, 330 atm. So now that we know the partial pressures, we can plug it back in to the Kp expression. So 0.330 times 0.330 equals 109. So 9 there. That's my Kp. Then to find Kc, I'm going to say that Kc is equal to Kp over RT delta N. You can use the other equation if you prefer. It really doesn't matter. You're going to get the same answer. So that's equal to 0.109 divided by 0.0821 times 298. All that raised to the delta N. In this case, products, there's 2 gas particles, reactants, no gas particles, so 2 minus 0, which is 2. And so Kc ends up being 1.82 times 10 to the power of negative 4. Let's look at letter B. So for B it says more NH3 is injected. When the equilibrium is reestablished, because you've added more of your products, so that disturbed the equilibrium. So according to Le Chatelier's principle, which way would it shift? Yep, it would shift to the left. So it shifts to the left until you reestablish a new equilibrium. And so when equilibrium is reestablished, the partial pressure of ammonia is twice the partial pressure of the hydrogen sulfide. We want to know what the new partial pressures of the 2 products are. So again, I know that Kp is equal to the partial pressure of ammonia times the partial pressure of the H2S. I always write the equilibrium expression whenever I'm talking about equilibrium. Then I figure out what I want to do. I also know from this that when I've reached equilibrium, the partial pressure of ammonia is twice that of the partial pressure of H2S. And so if I say that this is X, then this would be 2X. And then I also know that Kp, because it's a constant and we're at the same temperature, doesn't say anything about changing the temperature, Kp will always remain the same. So it's still the same as what it was in A that we calculated. So I know that Kp is 0.109. I know that this is 2x, and I know that this is x. So then that's 2x squared. So I divide the 0.109 by 2 and then take the square root of it. So I get x is equal to 0.233. And in this case, whenever you're finding the partial pressures or you're finding the concentrations, you have to have units. K, we don't need units for, but if you're finding concentration or pressure, you gotta have units. So in this case, it's ATM. So then the partial pressure of H2S is X, so 0.233 ATM. The partial pressure of the ammonia is 2X, so 2 times 0.233, so 0.466 ATM. So here are my 2 answers. Okay, let's look at part C. It says NH3 and H2S are introduced into a 1 liter flask at 25 Celsius. So this is a separate reaction. Or I should say it's the same reaction, but it's a separate vessel. It's a separate experiment now. So in this case, actually, my reactants are NH3 and H2S. I'm putting them together. And so they're going to form NH4HS. So it's kind of the reverse reaction, basically. So anyway, I'm going to take some ammonia, I'm going to take some H2S, put them together in a 1 liter flask. It says the initial partial pressure of each gas is 0.5 atm. So I'm going to take enough ammonia that it has 0.5 atm as its partial pressure, enough H2S that it has 0.5 atm as its partial pressure. Going to mix them together. They're going to react. Some of the NH3 and the H2S will react together to form some NH4HS. And I want to know how many moles of NH4HS will be formed when we reach equilibrium. So let's start by writing this reaction. So I have NH3 and H2S yielding NH4HS. I know that initially I have 0.5 ATM. I'm not going to use stick fix here, but you want to make sure that you keep track of them. So initially I have 0.5 ATM of NH3, 0.5 ATM of H2S. This is a solid, so it doesn't have any partial pressure. It doesn't really matter at all. I'm going to go ahead and write my Kp expression because, well, actually, I'll leave that for now, in a second. I'll come back to that. So I know that I'm starting out with 0.5 atm of each. Some of these will get used up to form NH4HS. The question is how much of this will get formed. So let's say that an X amount of this is going to get used up. So let's do an ice chart. So minus X. If NH4HS was a gas, it would be plus X, but again, it's a solid, so I don't include it in my ice charts at all. So at equilibrium, this is 0.5 minus X. This is 0.5 minus X. Now, to proceed, you can think of it as two different ways. And I hope this doesn't confuse anybody. So one way is you can say, well, Kp for this reaction as written is going to be 1 over the partial pressure of NH3 times the partial pressure of H2S, right? Or you can think of the reverse reaction, the one that we had earlier. So the one where it's, let me write that in a different color. So NH4HS yields NH3 plus H2S. So this is the reaction that we had before, the one in red, right? And Kp for that was the partial pressure of NH3 times the partial pressure of H2S. And we figured out that that's 0.109. Okay? So, you can use this expression and say that the partial pressures of these two is equal to 0.109, and that this we figured out at equilibrium is 0.5 minus X, and this is 0.5 minus X. So um, 0.5 minus X times 0.5 minus X is equal to 0.109, and solve for X. Can do it that way. In that case, you're going to get that X is 0.170 ATM. It's one way to do it. Or you can look at the equation that we have, this one, which is the reverse of that one. And so Kp for this reaction is the reverse or 1 over Kp for this reaction. So that is equal to 1 over 0.109. So you can say that 1 over 0.5 minus x times 0.5 minus x equals 1 over 0.109. In that case, x will also be 0.170 ATM. Hopefully I didn't lose anybody there. There are two different ways that you could think about it. Both will get you the same answer. Whichever you prefer, go with that. So let me go over that real quick again, the difference between the two, which again, you pick whichever way you want to. This is the equation, this is the reaction that we're talking about, which is the reverse of the earlier reaction. We have Kp for this reaction. And so you can write the expression for this reaction and say this is equal to 0.109. And at equilibrium, the constant, the pressures of these is 0.5 minus x each. So plug them in and solve for what x is. Or you can think of what's really happening, that the NH3 is reacting with H2S. So you're looking at the reverse of this one. And so your Kp for this reaction is 1 over these, which is 1 over 0.109. And so you can solve for x in this case, and again, it will be 0.170. So whichever way makes sense to you, do it that way. You can write both in your notes if you prefer, or you can pick one. Anyway, you get either way that x is 0.170. Now, what is x? What is x? X is how much pressure was lost either from the NH3 or from the H2S. It doesn't matter which one you look at. Let's look at the NH3. It's how much pressure you lost from the NH3 in order to make NH4HS. So that's how much actually reacted. Okay, so this, let's write a little note next to it. This is the pressure lost to make the NH4HS. Either by the ammonia or the H2S. All right, so now what? So now, since we have pressure that was lost, what we could do is we can use PV equals nRT to find out how many moles of ammonia reacted, how many moles of ammonia were lost, and we can use stoichiometry to get moles of NH4HS. So let's do that. So PV equals nRT. For the pressure, we're going to use the pressure that was used up, so 0.170 ATM. It's a 1 liter container. N is what we're looking for. R is 0.0821 ATM times liters per mole Kelvin. And this is at 298 Kelvin. N is equal to 0.00695 moles. And again, you could do this for either ammonia or for H2S, either one, it's X. But again, that X stands for how much was lost or used or reacted to form my NH4HS. So now I can use stoich. So 0.00695 moles of ammonia. On the bottom, moles of ammonia. On top, moles of NH4HS. It's a 1-to-1. So 0.00695 moles of NH4HS were formed. Now, why is it that I did this step? Why didn't I just say, well, this is plus x? And just say that x is how much NH4HS it's formed. I'd get the same number, right? But chemistry, in terms of chemistry principles, that does not make any sense because, well, you can't form any pressure when you form a solid. So that would not be correct. Or why didn't I say, well, I can do PV equals nRT and solve for the N for NH4HS? No, because this is the ideal gas law. So again, if you made a mistake like this, you might get the correct answer because it's a 1-to-1-to-1 ratio. But if you look at your work, it would not make sense because this is the ideal gas law. You can't use it for a solid. So you gotta do all these steps here. That's a pretty good question there. All right, the very last question in the packet here. Let's look at it. Nitric acid, HNO3, often has a brown gas, NO2, over the liquid. An NO2 molecule can bind to another NO2 molecule to form a dimer. So dimer means two bonded together. Like polymer is many bonded together. Dimer would be just two bonded together. So NO2 and its dimer, N2O4, are in equilibrium where N2O4 can dissociate to form or decompose to form 2NO2. And they give us Kp is 0.11. If the total pressure of the equilibrium mixture is 1.5 atm, what is the partial pressure of each gas? All right, so let's think about where to start here. So we have N2O4 decomposing to form 2NO2s. Since we're talking about equilibrium and they give us Kp, let's write the Kp expression. It would be the partial pressure of the NO2 squared divided by the partial pressure of N2O4. What are we trying to find? We're trying to find the partial pressure of each gas. So we're trying to find the partial pressure of the NO2 and the partial pressure of the N2O4. We are given what Kp is. Kp, they tell us, is 0.11. But we don't know either one. Can we relate between them? Well, we know that P total is 1.5 atm, which is the partial pressure of the N2O4 plus the partial pressure of the NO2, right? If you add them together, that's a total pressure. Now, can I say that the partial pressure of this is twice the partial pressure of this? A lot of people do that. The answer is no. Why not? Why not? Because we had ones before where, for example, A yields B plus C, and we'd say that the partial pressure of B is equal to the partial pressure of C because it's a 1-to-1 ratio. So why can't we apply that now? The reason is, here, at the beginning of this reaction, you had no B or C, right? So these were 0. As you decomposed A, you formed B and C, and they formed with the same ratio. So for every mole of B, you formed a mole of C. Excuse me. Now let's look at this one here. For every mole that's decomposed of N2O4, you form 2 moles of NO2. However, this is not a reaction that goes to completion. This is a reversible reaction. That's why we're doing this whole equilibrium thing. Which means I don't know how much of this actually decomposes. Like if I start with 1 atm of this, maybe 0.2 atm decomposes. Maybe 0.3 atm decomposes. Maybe 0.4 atm decomposes. But I don't know how much of it decomposes. So what's decomposed, yes, is 1 to 2 ratio with what's formed of this. But the total, I can't relate them. If 0.2 atm of this decomposed and I had 1 atm, then I'd have 0.8 atm of this left. And 0.4 atm of that one formed. Hopefully that makes sense. So again, because this is a reactant and this is a product, I can't relate these two at equilibrium. I can only relate their change. How much of this decomposes versus how much of this forms. I can relate that. That's a 1 to 2. But I cannot relate the total concentration or the total pressure of each of these at equilibrium because I don't know how much of this actually reacts. So I can say that the partial pressure of this is double that. What can I say? Well, I don't know. I don't know much other than this. But from this, I can say, well, if the partial pressure of NO2 was X, was some number, then the partial pressure of the N2O4 would be 1.5 minus X. Does that make sense? Or you could do it the other way. You could say the partial pressure of the N2O4 is X, so the partial pressure of this one is 1.5 minus X, because I know that when you add them together, the total would be 1.5. So I can use these to plug them back in here. So let me do that. So we set the top one to X, so X, and then don't forget the square, divided by 1.5 minus X. I'm going to let you take a minute to plug that in and solve for X. When I plugged it in, I got X to be 0.4 atm. And so we said that the partial pressure of the NO2 is X. So the partial pressure of NO2 is 0.4 atm. The partial pressure of the N2O4 is 1.5 minus X. So 1.5 minus 0.4 is 1.1 atm. That concludes the notes for this chapter. I hope you have a great rest of your day. See you guys soon.